Section 3.7 Linear Transformations. Consider two subspaces B a subset of Rn and W a subset of Rm. Subsets, well, not subsets, subspaces. Subspaces we say that a function we say that a function with domain in B and codomain in W is a linear transformation if it satisfies two conditions. T of x plus y is the same as T of x plus T of y. And T of c times x is the same as c times T of x. Remember that we're talking about vector spaces or well, subspace of vector space. But the point is that this, remember, this amount is the scalar multiplication. So C is supposed to be a real number, a scalar. Examples. Consider the transformation from T that goes with domain in R2 and codomain in the same subspace R2. This transformation is going to be defined as T of xy is equal to x plus y, x minus y. So, some comments about this. A linear transformation is a function, right? So the knowledge or the information that you have for functions is going to be maybe it's going to be very useful here. So if the domain is R2, this means that this function is going to choose values, or well, it's going to choose elements in R2. So in R2 we have pairs xy. So T of xy returns x plus y, x minus y. Yeah, returns something in R2 because the domain is R2 and the codomain is R2. So we will verify T is a linear transformation. All right, so I have to verify that the two conditions for linear transformation, this one and this one, they are true. The first one, I need to choose two elements, x and y, and show that when I add them and then I apply the transformation, it's the same as if I add them separately. So consider x. If I'm choosing one element x in the domain, must be from R2. So it should have the form x1, x2. And y, other element, again, is in R2, should have the form y1, y2. Then t of x plus y is t of x1, x2 plus y1, y2. These are vectors from vector spaces, so I can add them with the, as we know how to add in R2. So this becomes equal to t of x1 plus y1, x2 plus y2. So the first element, the second element. Now notice, this transformation, what does it do? It returns two components. The first one, you add the two components, and the second one, you subtract the two components. So I have to add these two, and then in the second one, subtract these two. So this is going to be so I'm going to continue. Next page is going to be t of x1 plus y1, x2 plus y2 will be equal to x1 plus y1 plus x2 plus y2. Yeah, because I have to add the two entries. This is the rule for the transformation. You see, t of xy is add them first and then subtract them. And then x1 plus y1 minus x2 plus y2. And then we can manipulate this. I have to show that it is equal to t of x plus t of y. T of x, notice, t of x would be t of x1, x2 will be x1 plus x2 and x1 minus x2. So this right now here, all of this inside, these are real numbers, so I can manipulate them. So this is going to be, notice, x1 plus x2 plus y1 plus y2. Yeah, I am manipulating this part. And here in the bottom, I should have x1 minus x2, but I can. I mean, I can do it. I mean, because I have x1 minus x2. You see this? So I can put here x1 minus x2 plus, should be here, y2. I mean, y1 minus y2. That okay? So, but these are elements of R2. So this is the same as x1 plus x2 plus x2, x1 minus x2 plus y1 plus y2, y1 minus y2. Because this is how we add elements in R2. But this is only, but notice, this is only t of x1, x2, x1, x2, plus t of y1, y2. Or what is the same? This is only t of x plus t of y. So yes, in this case, we have shown that t of x plus y is the same as this. T of x plus y is the same as t of x plus t of y. So we have shown that the first part for linear transformation is true. Now we have to verify the second one. Now, if C is a scalar, then we start with T of C of x, T of C times x. T of C times x is the same as T of C times x1, x2. Or what is the same? Because again, these are elements in R2. So how do we do this scalar multiplication in R2? Well, multiply each element. So it will be cx1, cx2, and now apply the transformation. The transformation is add the elements and then subtract them. So I have to add them here. Is cx1 plus cx2, and in the bottom, cx1 minus cx2. But notice, I have the c. I can factor the c. So this is the same as c times x1 plus x2, x1 minus x2. What is the same? This is the same as c times t of x. So again, we have verified in this case that t of c of x is the same as c t of x. So yes, t of xy equal to x plus y, x minus y is linear. It's a linear transformation. Other example. This is the first one. Other example, let me add a new page. Part B. Consider the transformation defined by t of x is equal to the 0 vector for any x in Rn, for any x in the domain, for any x that is here. I mean, this transformation will return only the 0 vector. No matter what vector x you have here, always when you apply this transformation, always is going to return the 0 vector. this transformation is linear. Notice, we will show t is linear. Why? Because t of x plus y is equal to the zero vector. Or what is the same? T of x plus t of y. Because these two, they are the zero vector as well. And the zero vector plus the zero vector is the zero vector. Because again, the key is that no matter what you introduce here into this transformation, always returns the same. So this is the property number one. And the property number two, t of c of x, is again the zero vector. But c the same as c times t of x. This is c times the zero vector. And a scalar times the zero vector is the zero vector. So t of x plus y is the same as t of x plus t of y. T of c of x is the same as c t of x, dx. So yes, we have this transformation is linear. This transformation is called the zero transformation. Always returns zero. Now, let's see one example from the assignments in web work. This is the part B. This one is going to be the part C. All right. Example. I'm going to read this part. These are the solutions, right? This is one of the exercises that you see in web work, but of course, the numbers maybe they're going to change in your case, but the process of the solution should be the same. We have a transformation from R2 up to R2, linear transformation that sends the vector u phi 2 into 2 1 and maps b 1 3 into 1 negative 1 3. Use properties of a linear transformation to calculate the following. Enter your answers are ordered pairs. All right. So notice, what do we know about this transformation? We don't have the formula in this case for the transformation, but we do know that it's linear and that t, it says, sends the vector phi 2 into 2 1. So if I apply the transformation to phi 2, well, I put it in this way. T of phi 2 is equal to the vector 2 1. That is the meaning for this. Sends the vector phi 2 into 2 1. And the vector b, I'm sorry, let me write like this. T of u is t of phi 2 that is equal to 2 1. And t of b, that is t of 1 3 is equal to negative 1 and 3. Negative 1 and 3. This is what we know, yeah, from the information given here, and here. Maps 1 3 into negative 1 3. So this means that when you apply the transformation to 1 3, it returns negative 1 3. Now, use properties of a linear transformation to calculate the following. For example, t of negative 3u. What is t of negative 3u? Well, we don't have the formula, but we know what t of u is. T of u, we have it here, and t of v, we have it here. So because of this is linear, since this is linear, I can apply the properties for a linear transformation. When you multiply scalar times a vector, you can take the scalar outside. So this is going to be negative 3 times t of u. But what is this? Negative 3 times what is t of u? T of u is 2, 1. So it will be negative 3 times 2, 1. And this is going to be multiplied with this scalar multiplication would be negative 6 comma negative 3. You see? Is the answer we have here. Now, t of 6b, the same. I can, since this transformation is linear, I can take out the 6, so it will be t 6 times t of b, and this would be 6 times what is t of b? T of b is negative 1, 3. So it will be 6 times negative 1, 3. Will be negative 6 comma 18. The answer we have here, you see? And finally, t of this. Well, this is the first one. Now, what is t of negative 3u plus 6b? Again, we know this is linear, so I can distribute the transformation into the two terms. I mean, this is going to be t of negative 3u plus t of 6b. But I already have what these values are, right? T of negative 3u is negative 6, negative 3, and this is negative 6, negative 18. So this becomes negative 6, negative 3, plus negative 6, negative 18. Because this value is this one, and this value is this one, you see? So only use these values. And then we have the addition of two vectors, add them as you know. It will be the first element with the first element, negative 12, comma, negative 18. Oh, I'm sorry. I think I did a mistake here. This is 18, right? Positive 18. Yeah, I'm sorry. So this will be positive 18. So negative 3 plus 18 is 15. And there you have. This is the answer. Very well. Other example. This is directly also from Wegborg. So we have now a transformation, a linear transformation from R3 up to R3, such that, notice again, we don't have the formula for the transformation, but we do have what is some elements here. I mean, for example, t of 1, 0, 0, it returns negative 1, and negative 2. So the question is, what is t of negative 1, 3, and negative 3? All right, so we start in this way. First, notice, remember that this vector, negative 1, 3, and negative 3, can be expressed in terms of the canonical standard base. Would be -1 times E1 plus 3 times E2 minus 3 times E3. But remember this vector, they were -1, 1, 0, 0, plus 3, 0, 1, 0, -3, 0, 0, 1. We have seen this vector before. Remember these vectors E1, E2, E3, they form the standard canonical basis. Right, but so I can express this vector in this way, you see? And in this case, it's going to be useful because I know what I have the information for each of these. I mean, notice I have T100, T010, and T001. So now I can apply the properties for transformation, for linear transformations. This is T of -1, 3, -3 is the same as T of all of this, -1, 1, 0, 0, plus 3, 0, 1, 0, minus 3, 0, 0, 1. And this becomes since this transformation we know is linear, so I can distribute the transformation into every term. So this would be T of -1, 1, 0, 0, plus T of 3, 0, 1, 0, plus T of -3, 0, 0, 1. You see? I applied the transformation to each of the terms. Now, in linear, I can take out the scalars. So this would be -T of 1, 0, 0, plus 3, T of 0, 1, 0, minus 3, T 0, 0, 1. You see? I took out the constant, this negative sign, this 3, and this -3. So now I have T of 1, 0, 0, T of 0, 1, 0, and T of 0, 0, 1, but I have the value for each of these vectors. So this becomes negative, -1, -1, -2, plus 3, -4, -1, 4, -3, -3, 2, 0, and this becomes 1, 1, 2, plus -12, -3, 12, minus -9, 6, and 0. And finally, only add them. Just be careful with this negative sign that I left there. So this is going to be 1 minus 12, -11, plus 9 is -2. 1 minus 3, -2, minus 6, -8. And 2 plus 12, 14, minus 0, 14. There you have it. The same answer as we have here, you see? So I use the properties for linear transformations. All right. Other example. Consider the matrix -6, 8, -5, and 3. Based on this matrix, I'm going to define a linear transformation that goes from R2 to R2. How? T of x is going to be equal to the matrix times x. And notice, this is well defined always because this matrix has size 2 by 2. So when I multiply times a vector that has size 2 by 1, 2 by 2, 2 by 1, always this is going to return a vector with size 2 by 1. You will see that. But I mean, this matrix because of this multiplication, because remember the how to multiply matrices, this transformation is well defined. So now let's find some values. What is t of 2, -2? Well, t of 2, -2 would be a times 2, -2. But A is a matrix, so it would be -6, 8, -5, 3, up to -2. You see? Because this transformation is multiply the matrix times the given vector. The given vector is this, so multiply the matrix times the vector. And this multiplication, as I mentioned before, is always possible. I have a 2 by 2 matrix, and this is a 2 by 1 matrix, or it's a vector, right? So this becomes -6 times 2, -12, plus -16. And in the bottom, -5 times 2, -10, minus 6. And this becomes -28, -16. You see, we obtained a matrix 2 by 1, or a vector, a column vector. Now, what is T of AB? T of AB, they are only it's a representative of a vector of with two components. So this is going to be A times AB, or this matrix that is -6, 8, -5, 3, AB. But this is only -6A plus AB, -5A plus 3B. There you have. This is in Wegboard, you will find an exercise similar to this as well. All right. Now, before we see more examples, I want to mention a theorem. If we have a linear transformation from Rn to Rm, consider the standard canonical base in Rn. This is the base E1, E2, and so on up to En. If A is the matrix defined by T of E1, T of E2, and so on, T of En, then we can define then the transformation defined by T of X equal to AX So what is the meaning for this? Always we can define a matrix with linear transformation, and the linear transformation that we have defined here is going to be equal to multiply the matrix times the given vector. So in other words, we are saying here that any linear transformation is essentially a matrix multiplication. So this theorem says that any transformation is the same as a matrix times the given vector when you apply the transformation. So essentially, when we're talking about linear transformations, we're talking about matrices. When we apply transformation, we're like applying matrix multiplication. But how to obtain this matrix A? We will see one example. Example. Let T be the linear transformation defined by this. Notice this transformation it goes from R2 to, because we have xy, and it has 1, 2, 3, 4 components to R4. So the canonical base here, canonical and standard base, of R2 is E1, E2. This is 1, 0, 0, 1. So I have to apply the transformation to the canonical base to obtain the matrix. The first one, T of E1 is T of 1, 0. And follow the rule. T of xy is 5y minus 9x. Here in this case, x is 1 and y is 0. So it would be 5y is 0, negative 9, comma, negative 3x, negative 3 times 1, negative 3, minus 0, negative 3, comma, 7 times x, 7 times 1 is 7, plus 2 times 0 is 0, comma, 6 times 1, 6. Negative 9, negative 3, 7, and 6. This is T of 1. T of E1. Now I need to apply the transformation to the other vector in the standard canonical base, in this case E2. So T of E2 is the same as T of 0, 1, and this is the same as, now the x is 0 and the y is 1. X is 0, y is 1. So 5 times 1 is 5 minus 0 minus 9 times 0 is 5. 5, comma, negative 3x minus y, negative 3 times 0, negative 1, comma, 7x plus 2y, 7 times 0, 0 plus 2y, comma 2. And times 6x times 0. 6 times 0, 0. So we have 5, negative 1, 2, and 0. Then, finally, when you create the matrix A, you will have to put this as columns, T of E1 and T of E2. So it would be negative 9, negative 3, 7, and 6, 5, negative 1, 2, and 0. You see? Negative 9, negative 3, 7, and 6, 5, negative 1, 2, and 0. And this is how you get the matrix based on a transformation, okay? The associated matrix. Definitions. If we have a linear transformation is a linear transformation we will define the range of T is the set of all the elements y such that y is equal to T of x for any x in the domain of T. Range. So the range of T is the set of all the elements that the function, well, in this case, the linear transformation returns. all the elements. When you choose one element in the domain and you apply the transformation to that element, that result is a member of the range. Range. Other definition. This is going to be the kernel or null space. With the same transformation, the kernel or null space is the set of all x in the domain of T such that T of x is equal to 0. So I want you to notice something. The range is a subset of the codomain, Rm in this case. And the kernel or null space is a subset of the domain. Yeah? All right. Example. Consider the matrix 1, 0, negative 1, 0. I would define a linear transformation by T of x equal to Ax. So T will be from R2 up to R2. One of the questions, one kind of problem that you can find in the assignments and the exercises from web work is the element 2, 2 in the range of T. So to respond to that, you will need to find an element x. We need to find x that I'm going to label x1, x2 in the domain such that T of x is equal to 2, 2. So what is T of x? T of x is only apply the transformation. It's going to be a T of x T of x is a times x. What is the same? 1, 0, negative 1, 0 times x1, x2. And this is equal to, apply the multiplication of matrices, is x1 negative x2. And this should be equal to the vector that I want, 2, 2. We're looking for x such that t of x is equal to this. But now we have this equation. This equation of vectors. So this implies, since these two are equal, this vector is equal to this. Remember, two vectors or matrices are equal if component by component they are equal. So from here we have two equations. x1 equal to 2 and negative x2 equal to 2, which implies that x2 is equal to negative 2. So if we define x as 2, negative 2, then t of x is going to be equal to 2, 2. So the answer is yes. So yes, 2, 2 is in the range of t. Why? Because we could be able to find a vector x, in this case 2, negative 2, such that when we apply the transformation, we obtain 2, 2. Is that okay? To show that one element is in the range, you need to find one element in the domain of the transformation, such that when you apply the transformation to that element in the domain, you obtain the value that you want. So in this case, we did it because that element in the domain is 2, negative 2. So yes, this is in the range. 2, 2 is in the range of t. Yeah. Now for the same problem. This is part A. Part A, I have it here. Part A. Part B, other question. Is the element 1, 1 in the kernel of T? Remember that the kernel of T is all the elements in the domain such that when you apply the transformation, you have the zero vector. So, if so, then T of 1, comma 1 should be equal to the zero vector. In this case, the zero vector is 0, 0. So this means T of 1, 1 is the matrix times 1, 1 should be equal to the zero vector, 0, 0. Or what it is saying, the matrix is 1, 0, negative 1, 0 times 1, 1 should be equal to 0, 0. So if this equation is true, then we can say that this element is in the kernel. We obtain two equations. It's like kind of weird. Yeah, three equations. We have, let me say it like this, we obtain true statements. So let's verify the computation here. So this implies Negative 1 times 1 is 1, plus 0 times 1 plus 0, negative 1 plus 0 times 1 plus 0. We have from the left side we obtain 1 and negative 1. That is equal to 0, 0? No, it's impossible, right? Impossible. Because 1, this implies that 1 should be equal to 0 and negative 1 is equal to 0. So we cannot have that. So this element 1, 1 is not in the kernel for this transformation. If it were in the kernel, then we should obtain an element, and we should have obtained 3 equations here, 0, 0 here, but we don't have it, right? So in this case, no. No. Since T of 1, 1 is different from 0, 0, then 1, 1 is not in the kernel. All right, that's all by now. Remember, you have questions, you can let me know. You can send me an email directly from WebWork. I reply to everything. Just please be patient. You gotta be patient because sometimes I have many questions to respond, but I will always reply to your questions. Is that okay? See you later.